So when you think about the solar system, what's the first thing that pops into your head? For most of us, right, it's this grand, majestic clockwork. You've got the planets all gliding along these perfect, predictable paths, a kind of cosmic ballet that's been going on forever and will go on forever. It's a really beautiful, comforting thought. And, well, it's also completely wrong.
And look, for centuries, this was the dominant scientific view. I mean, you had thinkers like Johannes Kepler, who were just so captivated by all this apparent order that they literally imagined the planets nested inside perfect geometric shapes. That's what you're seeing here with this Kepler's goblet. It was this vision of, a static, almost divine perfection.
But what if that harmony was just an illusion? What if the very things that seem to prove this perfect order were actually deep down the seeds of its own destruction?
All right, let's talk about this clockwork universe. Because this idea, it was way more than just a nice metaphor. It was a cornerstone of scientific thought for hundreds and hundreds of years.
This quote here really gets to the heart of it, doesn't it? It captures the absolute certainty of the era. Think about it. We had these huge triumphs, like predicting the return of Halley's Comet. Stuff like that seemed to prove it beyond a shadow of a doubt. The universe wasn't just orderly, it was completely calculable. A giant machine that, if we were smart enough, we could understand completely.
And that way of thinking, well, it leads to a pretty wild conclusion: determinism. This was an idea championed by the brilliant mathematician Laplace. And his whole thing was, if you could just know the exact position and velocity of every single particle at one moment, then the entire future of the universe is perfectly predetermined. You could predict everything that's ever going to happen, and you could even reconstruct the entire past. It's like the cosmic movie was already written, and we're just watching it play out.
Okay, but here's where the story takes a turn. Here's the twist. It turns out the very evidence for this beautiful, perfect order, it contained a hidden paradox, a secret that would eventually just shatter that whole clockwork dream.
So what's the cause of all this hidden chaos? It's something called orbital resonances. Now, these are basically just simple, neat integer relationships between the orbits of planets. A great example is Jupiter and Saturn. For every 5 times Jupiter goes around the Sun, Saturn goes around about twice. And for a long time, these simple relationships were seen as the ultimate proof of cosmic harmony, the perfect music of the spheres.
And this is the central paradox, the thing that just blows my mind. The very thing that we thought was the source of order is actually the engine of chaos. See, a single perfect resonance on its own can be totally stable. But in a really complex system, like our solar system, you've got multiple resonances, all starting to overlap and interfere with each other. It's like, imagine you have a perfectly clean, simple rhythm, and then another, slightly different rhythm starts playing over it. The simple patterns just break down, and all that beautiful order descends into this tangled, unpredictable mess.
Okay, I know this idea can feel a little abstract. So to make it super concrete, let's just dial it way back and look at a much, much simpler system, a pendulum.
So the simple back and forth swing of a pendulum, it's the poster child for predictability, right? This chart you're looking at is called a phase portrait, and it basically shows all of the pendulum's possible motions. Those oval paths there in the middle, that's the familiar swing, and the wavy lines at the top and bottom, that's what happens when it swings all the way around. The point is it's smooth, it's regular, and it's perfectly predictable. This is our perfect model for a single, stable resonance.
But what happens if we mess with this perfect system? Just a little bit. We're not talking about a random push. We're talking about a tiny, regular, repeating nudge, what scientists call a periodic perturbation.
And boom, this is the result. Just look at that transformation. On the left, you've got that perfect, predictable order of a single resonance we just talked about. But on the right, the moment we add that tiny, repeating nudge, those beautiful, clean lines just shatter. They shatter into this incredibly complex, messy pattern.
Yeah, those smooth, predictable paths completely dissolve into what's called a chaotic sea. It's just a messy, scattered region. And inside the sea, the true hallmark of chaos appears: sensitive dependence on initial conditions. What that means is 2 starting points so close together you can barely tell them apart will end up on wildly different paths, and that makes any kind of long-term prediction totally impossible.
So you see, chaos isn't just, messiness. It's a fundamental limit on what we can know. Which of course raises a huge question. Can we measure it? Can we actually put a number on how far into the future we're able to predict? And it turns out we can. It's called the Lyapunov time. The easiest way to think about it is as a predictability horizon. For any chaotic system out there, this is the timescale after which our predictions pretty much become pure guesswork. Any tiny error in our initial measurement blows up so fast that we've lost any and all useful information.
All right, so now that we have this concept, this Lyapunov time, let's go hunting for chaos right here in our own cosmic backyard. Is this all just some weird theoretical thing, or can we actually see its effects out there?
First up, Exhibit A, Saturn's moon, Hyperion. This thing is kind of lumpy, almost potato-shaped, and it doesn't spin smoothly like our moon does. Nope, it tumbles chaotically. And we can actually see this because its brightness varies in a totally unpredictable way. And get this, its predictability horizon, its Lyapunov time, is just about 30 days. That's it.
Now, this next one shows that chaos isn't just about tumbling, it's a powerful sculptor of the solar system. Exhibit B, the Kirkwood Gaps, in the asteroid belt. These aren't just random empty spaces, not at all. They are specific zones where Jupiter's massive gravity creates these powerful resonances, and those resonances create chaos. Any asteroid that wanders into one of these gaps gets destabilized and just flung right out of the belt.
And we can even see the ghosts of chaos from the past. I mean, check this out. The orbits of Uranus's moons, Miranda and Umbriel, they show these telltale chaotic layers. It's evidence, a ghost of a time way back in the distant past when they were trapped in an unstable resonant dance. The chaos itself might be over, but it left its fingerprints all over the crime scene.
Okay, so we've got chaos in moons, we've got chaos in asteroids, we've got chaos in satellite systems, which obviously leads us to the big one, the main event. What about the planets themselves? What is the Lyapunov time, the predictability horizon for the motion of Earth, Mars, Jupiter, the whole shebang? The answer is about 5 million years. Seriously, let that sink in for a second. Our solar system is 4.5 billion years old, and we're saying its future is fundamentally unpredictable beyond a mere 5 million years. That's just a tiny fraction of its total age. It's like 0.1%. The old idea of a perfect clockwork universe, it's not just cracked, it's shattered.
So, what's the big deal? Why does this matter? Well, it matters because our entire picture of our cosmic home has to change. It's not this static, forever stable machine we once thought it was. Its long-term future is fundamentally unpredictable. And the main drivers of this instability? It's the giant planets, especially Jupiter and Saturn, with their immense gravity and all those interacting resonances. The bottom line is this: chaos isn't some weird anomaly. It's a fundamental feature. It's woven right into the fabric of our cosmic home.
And this quote here, from the author of the paper we're looking at, just says it all, really. That old idea of full predefiniteness, of perfect predictability, it was fundamental for centuries, but it's gone. Now we know that the time of predictable motion for anybody in the solar system is limited. We live in a universe where we know for a fact that our knowledge has a horizon.
And that really leaves us with one final massive question to chew on. If our own cosmic backyard, the place we know best, the place that once seemed like the very symbol of perfect order, is actually fundamentally unpredictable on a long enough timescale, what does that say about everything else? What does that imply about the countless other planetary systems out there, about galaxies, about the grand structure of the entire universe?